Pick up any electronic device, your phone, your laptop, the remote control on your coffee table. Somewhere inside it, probably in several places, there is a ceramic component. You cannot see it. It has no moving parts. It generates no signal. It processes no data. It does exactly one thing. It keeps electricity from going where it should not go. That function sounds trivial. It is the most underappreciated function in all of engineering. Without it, there are no circuits. Without circuits, there are no radios, no radars, no computers, no telecommunications, no electronic devices of any kind. The insulator is the silent partner in every electrical system ever built, the component that exists only to prevent disaster, that is noticed only when it fails, that receives credit for nothing and blame for everything. It is the difference between a circuit that works and a circuit that burns, between a radio that transmits and a radio that shorts out, between a radar set that detects an incoming bomber at 50 miles and a radar set that catches fire the first time someone turns it on, between a proximity fuse that detonates at exactly the right moment and a dud that buries itself in the mud. The ceramic component that performs this invisible, unglamorous, absolutely essential function is called an insulator. And in 1942, the United States military discovered that it did not have nearly enough of them, that the ones it had were often the wrong kind, and that the entire American war effort, every radio, every radar, every piece of electronic equipment that the most technologically advanced military on Earth depended on was bottlenecked behind a material that most people had never heard of and could not pronounce. That material was steatite. And this is the story of the company that saved the day. To understand why ceramic insulators mattered to the war, you first need to understand what was happening inside a military radio in 1942. And to understand that, you need to understand the vacuum tube. Every radio, every radar set, every piece of electronic equipment in the Second World War ran on vacuum tubes. There were no transistors, there were no integrated circuits, there were no microchips. The transistor would not be invented until 1947. In 1942, if you wanted to amplify a signal, generate a radio frequency, detect an incoming aircraft, or decode an encrypted message, you did it with vacuum tubes. Glass envelopes containing metal electrodes in a vacuum, heated by glowing filaments, controlling the flow of electrons through empty space. A military radio set like the SCR-300 backpack walkie-talkie contained roughly a dozen vacuum tubes. The SCR-299, the mobile communications truck that served as a division's primary radio link, contained far more. A shipboard radar system like the Mark IV fire-controlled radar contained dozens of specialized tubes, some of them operating at power levels that would vaporize a civilian radio set. The cavity magnetron, the British-invented heart of microwave radar that had been shared with the United States under the Tizard mission in 1940, operated at power levels measured in kilowatts and frequencies measured in gigahertz. The tubes that amplified, mixed, detected, and generated these signals were precision instruments made of glass, metal, and vacuum, operating at temperatures that would blister skin and voltages that would kill on contact. A B-17 bomber carried multiple radio sets and radar equipment containing scores of tubes between them. A destroyer or a cruiser might have hundreds of vacuum tubes aboard across its communications, radar, fire control, and sonar systems. A fleet carrier had thousands. The American military consumed vacuum tubes by the tens of millions during the war, and every one of those tubes required ceramic insulation at multiple points in its installation. Each of those vacuum tubes had to be mounted in a socket, and each socket had to be made of a material that could withstand the heat generated by the tube's filament, which could reach several hundred degrees without conducting electricity. The socket had to insulate the tube's pins from each other and from the chassis of the radio, preventing the high voltages inside the tube from leaking to ground or arcing between circuits. If the insulation failed, the tube shorted out. If the tube shorted out, the radio died.
If the radio died, the soldier, the sailor, the pilot lost contact with everyone who could help him.
But the sockets were only the beginning. Inside every radio and radar set, there were dozens of other places where electricity had to be kept from going where it should not go. Terminal strips where wires were connected, standoff insulators that held components away from the metal chassis, feed-through insulators where signals passed through metal bulkheads, coil forms around which inductors were wound, capacitor housings, antenna strain insulators that held guy wires under tension while preventing electrical current from traveling down them. Every one of these components required an insulating material that could withstand heat, resist moisture, maintain its electrical properties at high frequencies, and survive the mechanical punishment that military equipment endured in combat. In the peacetime electronics industry, many of these components were made from bakelite, a phenolic resin that was cheap, easy to mold, and adequate for consumer applications. A tabletop radio in a living room in Iowa did not need to survive artillery vibration or tropical humidity. Bakelite was fine for that. Military equipment was different. Bakelite softened at high temperatures. In the engine compartment of a tank in the North African desert, where ambient temperatures could reach well over 100 degrees Fahrenheit before the engine even started, bakelite components warped and lost their insulating properties. In the Pacific, where humidity levels exceeded 90% for weeks on end and rain was a near-daily occurrence, bakelite absorbed moisture like a sponge. Wet bakelite conducted electricity. A radio insulator that conducted electricity was worse than useless. It was actively destructive, creating short circuits and spurious signals that could render an entire radio set inoperable. Reports flooded back from the Pacific theater of radio failures traced to insulator degradation. Equipment that had worked perfectly in the factory in New Jersey failed within weeks in the jungles of Guadalcanal or New Guinea. The moisture penetrated the bakelite, the electrical resistance dropped, and the circuits developed leakage paths that the designers had never anticipated. Signal-to-noise ratios degraded, transmitter efficiency fell, receivers became deaf with stray currents. The problem was not the vacuum tubes or the crystal oscillators or the wiring. It was the stuff that held everything in place while keeping the electricity where it belonged. Bakelite also cracked under the kind of mechanical shock that a radio experienced when bolted to the inside of a tank crossing rough terrain or a bomber flying through flak-filled skies. And at the high frequencies increasingly used in military communications and radar, bakelite's dielectric losses became unacceptable. The signal energy that should have been transmitted was instead absorbed by the insulator itself, turning into heat and wasted power. At frequencies above a few hundred megahertz, bakelite was essentially opaque to radio energy. The military needed something better. It needed ceramic. Ceramic insulators were not new in 1942. Porcelain had been used for electrical insulation since the telegraph era. The high-voltage power lines that crisscrossed America hung from glazed porcelain insulators that had been manufactured in essentially the same way since the 1880s. But powerline porcelain was heavy, bulky, and designed for a single purpose: preventing electricity from leaking from a wire to a wooden pole. It was not suitable for the compact, lightweight, precision electronics that modern warfare demanded. The technical ceramics that the military needed had a complicated pedigree. Before the First World War, Germany had held a near-global monopoly on advanced ceramic insulator production. German companies controlled prices and production of steatite parts, spark plug insulators, and heating element mounts using raw soapstone from their own mines. When the naval blockade of World War I cut France and Britain off from German steatite supplies, it created an immediate crisis. France could not manufacture spark plugs for its military vehicles. The crisis forced the Allies to develop their own steatite capabilities, and companies like insulatite emerged to fill the gap. But even after the First World War broke Germany's monopoly, the German steatite industry remained the most technically advanced in the world through the 1930s. The Allies were now fighting an enemy whose ceramic engineering had been superior to their own for decades. What the military needed was a special class of ceramic called steatite, a material based on magnesium silicate, the same mineral family that includes talc and soapstone. Steatite ceramic was made by grinding talc, clay, and a flexing agent like feldspar or barium carbonate into a fine powder, pressing or extruding the powder into shape, and then firing it in a kiln at temperatures exceeding 1200 degrees Celsius. The result was a dense, non-porous white or gray material with properties that read like a wish list for an electronics engineer. Steatite had extremely high electrical resistance even at elevated temperatures. It had a high dielectric strength, meaning it could withstand high voltages without breaking down. Most critically for radio and radar applications, it had a very low dielectric loss factor at high frequencies. This meant that a steatite insulator did not absorb the radio frequency energy passing through the circuit. The signal passed by the insulator without being degraded. At the frequencies used in military radar, typically in the hundreds of megahertz and eventually into the gigahertz range, this property was not just desirable, it was essential. An insulator with high dielectric loss at radar frequencies would absorb so much energy that the radar set would be useless. Steatite was also mechanically strong, resistant to moisture, chemically inert, and could be formed into complex shapes with reasonable dimensional tolerances. It could be ground to precise dimensions after firing. It could be glazed to seal its surface against moisture penetration. It could be metallized, coated with a thin layer of metal to allow it to be soldered into assemblies. It was, in short, the perfect material for military electronics. And in 1942, there was almost no one in America who could make it in the quantities the war demanded. Before the war, the American steatite ceramic industry was tiny. It existed to serve the civilian electronics market, which was itself modest by wartime standards. A handful of companies scattered across the eastern United States produced steatite components for commercial radio manufacturers, telephone companies, and industrial electrical equipment makers. The entire industry might have employed a few thousand people. The company that would emerge as the dominant producer was the American Lava Corporation, based in Chattanooga, Tennessee. American Lava had been founded in 1902 by Paul John Cruzy, an electrical engineering graduate of Union College in Schenectady, New York. Cruzy's father, John Cruzy, was a Swiss immigrant who had worked directly with Thomas Edison at Menlo Park. The elder Cruzy was Edison's primary mechanic, the master craftsman who translated Edison's sketches and ideas into physical devices. He built the first phonograph with his own hands in 1877, working from Edison's rough drawings. When Edison spoke the words, "Mary had a little lamb," into the machine, and Cruzy heard the tinfoil cylinder play them back, the mechanic reportedly exclaimed, "Mein Gott in Himmel!" It was one of the most famous moments in the history of technology, and the hands that built the machine belonged to the father of the man who would build the ceramic insulator company that kept the Allied war machine connected. The son inherited the father's gift for precision manufacturing. American Lava initially produced what were called German lava burners, ceramic components for acetylene lighting equipment. The company was partly German-owned, and when the United States entered World War I, it was seized under the Alien Property Custodian Act and sold to American interests. Paul Cruzy purchased the company for $80,000 in December 1918 and began rebuilding it. Through the 1920s and 1930s, American Lava developed expertise in technical ceramics, materials engineered for specific electrical and mechanical properties rather than for household or decorative use. The company's signature product line was branded Alcimag, a name derived from the primary elemental components, aluminum, silicon, and magnesium. Alcimag ceramics were available in dozens of formulations, each optimized for specific applications. Some were designed for maximum electrical resistance. Others were optimized for mechanical strength or thermal shock resistance, or dimensional precision after firing. The catalog read like a periodic table translated into product specifications. The company's factory sat near rail lines and the Tennessee River in North Chattanooga, occupying a building that had once been a furniture warehouse. It was purchased in 1936 as the company anticipated growth. That anticipation proved prophetic. When war came, American Lava was one of the very few companies in the United States with the knowledge, the equipment, and the workforce to produce the steatite ceramic insulators that the military desperately needed. The demand hit like a tidal wave. Every branch of the military needed ceramic insulators, and they needed them in quantities that dwarfed the entire pre-war production capacity of the industry. The Signal Corps needed them for radios. The Navy needed them for shipboard electronics and radar. The Army Air Forces needed them for airborne radar and radio equipment. The emerging field of military electronics, which was growing faster than any other branch of war technology, consumed ceramics at a rate that no one had anticipated. The problem was not just quantity, but variety. Military electronics used ceramics in hundreds of different shapes and sizes. Tube sockets alone came in multiple configurations: 4-pin, 5-pin, 7-pin, 8-pin, 9-pin, and specialized designs for high-power transmitting tubes. Each socket required precisely dimensioned ceramic bases with holes for the tube pins, grooves for the contact springs, and mounting holes for attaching the socket to the chassis. Standoff insulators came in dozens of sizes, from tiny spacers a quarter-inch tall to heavy-duty posts several inches long. Antenna insulators had to be designed to withstand the specific mechanical loads of the antenna systems they supported. Every one of these components had to meet military specifications that were far more demanding than civilian standards. The ceramics had to maintain their electrical properties across a temperature range from Arctic cold to tropical heat. They had to resist moisture absorption in the humid climates of the Pacific Theater. They had to withstand mechanical shock and vibration that would shatter ordinary porcelain. And they had to be produced in quantities measured in millions of units per month. American Lava's factory in Chattanooga became a wartime production facility that bore no resemblance to the modest pre-war operation. The company expanded its workforce dramatically, eventually employing roughly 1,500 workers at peak production. Women who had never seen a kiln were recruited from farms across rural Tennessee and northern Georgia. Many of them had never worked in a factory of any kind. One worker later recalled that she had left the family farm because she did not want to pick cotton for the rest of her life. She rode the bus each day from her apartment in Highland Park to the plant in North Chattanooga, where she operated a kiln in the firing shop. Part of her training included classes at Kirkman Technical High School, because the precision required to fire ceramics to military specifications could not be learned from experience alone. The women had to understand temperature curves, firing schedules, shrinkage rates, and the visual cues that indicated whether a batch was progressing correctly. These women became the backbone of the production line, just as women became the backbone of ammunition plants, aircraft factories, and shipyards across the country. They did not weld ships or rivet aircraft fuselages. They shaped clay, loaded kilns, monitored temperatures, and pulled finished ceramic parts from the fire. The work was hot, repetitive, and demanded constant attention. A kiln that overheated by 50 degrees could ruin an entire batch. A batch that was ruined was tube sockets that did not exist, insulators that were not shipped, radios that were not built, soldiers who could not communicate. The company's wartime advertising, placed in electrical trade magazines under the Al-SciMag brand, showed tanks in combat with the tagline, "Where the going is toughest, you'll find Al-SciMag." The copy explained that tank radios had to be compact, dependable, and able to withstand terrific vibration, jolts, and jars.
They had to operate under extremes of heat and cold. They must not fail. That is why Allied tank radios were equipped with Al-Cimag steatite ceramic insulators. The advertising was not hyperbole. It was a factual description of the operating conditions that the ceramics had to survive.
The manufacturing process for steatite ceramics was a craft disguised as an industry. The raw materials, talc, clay, and flux, were sourced from domestic deposits. America, unlike its situation with quartz crystals from Brazil, manganese from India, or chromium from Africa, actually had adequate supplies of the mineral raw materials for steatite production. Talc deposits in New York State, Vermont, Montana, North Carolina, and California provided the primary ingredient. Clay came from deposits across the Southeast. Feldspar, the fluxing agent, was mined domestically in sufficient quantities. For once, the United States had the raw materials it needed within its own borders. The bottleneck was not mineral, it was human. Processing capacity, kiln capacity, and the expertise to transform raw minerals into precision electronic components. The powder was prepared by grinding and mixing the raw materials with water to form a clay-like body that could be shaped by pressing, extruding, or casting. For small, high-volume parts like tube socket bases, dry pressing was the preferred method. The ceramic powder, mixed with a small amount of organic binder, was fed into steel dies and compressed at pressures of several thousand pounds per square inch. The resulting green part, unfired and fragile, was a precise replica of the die cavity. For more complex shapes, extrusion was used. The ceramic body was forced through a die like toothpaste from a tube, producing long rods, tubes, and profiles that could be cut to length and further machined before firing. Some parts were produced by slip casting, pouring a liquid suspension of ceramic powder into plaster molds that absorbed the water and left a thin shell of ceramic conforming to the mold shape. After forming, the parts were dried and then fired in tunnel kilns, long continuous furnaces through which the ceramic parts traveled on refractory carts. The firing process took many hours, with the temperature carefully controlled through a cycle of heating, soaking at peak temperature, and slow cooling. The peak temperature, typically around 1200 to 1300 degrees Celsius, caused the mineral particles to sinter, fusing together into a dense, hard, non-porous body. The firing was the most critical step. Too low a temperature and the ceramic was porous and weak, with microscopic channels through which moisture could penetrate and destroy the insulating properties. Too high, and it warped, cracked, or fused to the kiln furniture, the refractory shelves and supports that held the parts during firing. The temperature had to be uniform throughout the kiln to ensure that every part in a batch met the same specifications. A variation of even 20 degrees across the kiln could mean the difference between parts that passed military inspection and parts that were scrap. The tunnel kilns that American Lava operated were continuous process furnaces, some of them over 100 feet long, divided into heating, soaking, and cooling zones. The ceramic parts, loaded onto refractory carts, entered one end of the kiln and emerged from the other many hours later, transformed from chalky, fragile greenware into dense, glass-hard finished components. The atmosphere inside the kiln mattered. A reducing atmosphere, low in oxygen, produced white ceramics, while an oxidizing atmosphere produced a yellowish color. The chemistry of the kiln atmosphere affected not just color but electrical properties, and the operators had to maintain precise control of the gas flow and combustion conditions throughout the firing cycle. The women who operated the kilns at American Lava's Chattanooga plant learned to read the color of the kiln interior through peepholes, judging temperature by the shade of orange or white glow from the heated ceramics and refractory walls. They listened to the sounds of the kiln, the hiss of gas burners, the subtle cracking of cooling parts, the change in pitch that indicated a temperature shift.
They developed an intuitive feel for the process that complemented the pyrometers and thermocouples that provided quantitative measurements. It was a craft as much as a science, and the best kiln operators were valued the way master glassblowers or expert welders were valued, for a skill that could be taught but not fully transferred without years of hands-on experience. After firing, the parts were inspected, ground to final dimensions where necessary, and tested for electrical properties. Parts that failed specification were rejected. The rejection rate in the early months of wartime production was significant as the industry struggled to scale up while maintaining the quality standards that military applications demanded.
The applications that drove the heaviest demand were radar and high-frequency radio. Radar was the transformative technology of the Second World War. It allowed ships to detect enemy vessels and aircraft in darkness and through fog. It allowed fighter controllers to vector interceptors onto incoming bombers. It allowed bombers to navigate and identify targets through cloud cover. It allowed submarines to be detected from the air. Every Allied advantage in situational awareness, the ability to know where the enemy was before the enemy knew where you were, depended on radar. And radar depended on ceramics. The magnetron tube, the heart of every microwave radar set, generated enormous amounts of radio frequency energy at extremely high frequencies. The insulating materials surrounding the magnetron and its associated circuitry had to be transparent to those frequencies, meaning they could not absorb the energy. Steatite was one of the very few materials that met this requirement. The waveguides that channeled the radar signal from the magnetron to the antenna used ceramic windows and seals. The antenna feed assemblies used ceramic standoff insulators. The receiver circuits used ceramic tube sockets and coil forms. A single airborne radar set contained dozens of ceramic components. A shipboard radar installation contained hundreds. The production of radar sets during the war numbered in the tens of thousands. Each one required ceramics that met specifications tighter than anything the pre-war industry had produced. The proximity fuse, one of the most closely guarded secrets of the war, was another massive consumer of ceramics. The proximity fuse was a tiny radar set built into an artillery shell, one of the most astonishing miniaturization achievements of the war. It contained a miniature vacuum tube oscillator, a detector circuit, and a battery, all packed into a shell casing roughly the size of a fist. The fuse transmitted a radio signal and detonated the shell when the signal reflected off a nearby target, typically an aircraft. The fuse had to survive being fired from a gun, which subjected it to accelerations exceeding 20,000 times gravity. At that force, a human body would be crushed to a thin paste. Every component inside the fuse, including the ceramic insulators that held the tiny vacuum tubes in their sockets and separated the circuit traces from the metal shell body, had to withstand that force without cracking, shattering, or shifting out of position by even 1/1000th of an inch. The proximity fuse program, classified as the third most important secret of the war after the atomic bomb and D-Day, consumed ceramic components by the millions. By the end of the war, American factories had produced over 22 million proximity fuses. Each one contained multiple ceramic insulating components. The specifications were among the most demanding in the entire war, and the ceramics industry that supplied them had not existed in any meaningful sense 3 years earlier. The German steatite industry had actually been more advanced than the American industry before the war. German companies, particularly the Steatite Magnesia AG group based in Bavaria, had dominated the global technical ceramics market in the 1920s and 1930s. German steatite was specified by electrical equipment manufacturers worldwide. German ceramic engineers had developed formulations and firing processes that American companies were still catching up to when the war began. But Germany's ceramic advantage eroded as the war continued, for the same reason that all German industrial advantages eroded: strategic bombing, raw material shortages, and the progressive collapse of transportation infrastructure. The ceramic factories needed coal or gas for their kilns, and both were increasingly scarce. They needed raw materials transported from mines and processing plants, and the rail network was being systematically destroyed. They needed skilled workers, and skilled workers were being drafted into the military. By 1944, German ceramic production was a shadow of what it had been in 1939, while American production was still climbing. Meanwhile, American production expanded relentlessly. By 1943, American Lava and the handful of other domestic producers, including companies like Steatite, Centralab, and Coors Porcelain, had scaled their operations to meet the torrent of military demand. American Lava alone employed roughly 1,500 workers at its peak, producing ceramic components around the clock for every branch of the armed forces. The production achievement was quiet and unglamorous. There were no dramatic photographs of ceramic production lines. No famous generals praised the insulator makers. No movies were made about the women who operated the kilns in Chattanooga. The ceramics simply appeared in the supply chain, flowed into the electronics factories, were assembled into radios and radar sets and proximity fuses, and went to war inside the equipment that every soldier, sailor, and airman depended on. Consider Normandy. On June 6, 1944, the invasion depended on radar to track the weather, to detect German naval vessels, to guide naval gunfire, and to coordinate the massive air armada that flew over the beachheads. The radios that connected the fleet to the shore to the headquarters, and the headquarters to the aircraft all contained ceramic insulators. The proximity fuses that burst naval shells above the German beach defenses, showering the positions with shrapnel instead of burying the explosive energy in the sand, contained ceramic components that had survived the 20,000 G launch from a naval gun barrel and then functioned perfectly at the moment of detonation. None of the men who stormed the beaches knew that their survival depended in part on a fired piece of magnesium silicate made in a factory in Chattanooga by women who had come from cotton farms. But it did. After the war, American Lava continued to grow. The explosion of civilian electronics, television, commercial radio, telecommunications, and eventually computers created ongoing demand for technical ceramics that exceeded even wartime levels. Every television set in every American living room contained ceramic components. Every telephone exchange used ceramic insulators. The post-war electronics boom was, in a sense, the peacetime dividend of the wartime ceramics buildup. In 1953, the Minnesota Mining and Manufacturing Company, better known as 3M, acquired American Lava in a stock deal. The acquisition was front-page news in the Chattanooga Times and was watched with anxiety by the 1,500 workers who depended on the plant for their livelihoods. The deal gave 3M entry into the technical ceramics market, and American Lava continued to operate as a subsidiary under local management. The workers were told their jobs were safe. For a time, they were. The Cold War created its own surge of demand. Missile guidance systems needed ceramic insulators that could survive the vibration and acceleration of a rocket launch. Satellite electronics needed ceramics that could function in the vacuum and radiation environment of space. Nuclear weapons required ceramic components for their detonation circuits. The military-industrial complex that President Eisenhower would later warn about consumed ceramics in quantities that dwarfed even the Second World War because the electronics of the Cold War era were orders of magnitude more complex than anything that had existed in 1945. American Lava's Chattanooga plant remained in production through the 1950s, 1960s, and 1970s, employing generations of workers from the surrounding community. In 1963, part of the operation was transferred to Lawrence, South Carolina, in a move that foreshadowed the plant's eventual decline. Workers who had spent decades in Chattanooga were asked to uproot their families and move to a new state. Some went, many stayed, and found that the plant they stayed for was slowly shrinking. In 1981, 3M closed the main Chattanooga plant, shifting production to other facilities. The closure was announced with a banner headline in the Chattanooga News Free Press on February 4, 1981, 3M to close main plant here. It was a blow to the local economy and the end of an era for North Chattanooga. The building that had been a furniture warehouse before it was a ceramics factory, the building where Paul Cruzy had built a company on the legacy of his father's work with Edison, the building where women from cotton farms had learned to fire kilns and shape clay into the components that held the electronic nervous system of the Allied war machine together, became a memory. The workers who had made the insulators scattered into other jobs, other industries, other lives. Some retired. Some moved to the Lawrence plant. Some found work in Chattanooga's other industries. A reunion was held years later, and the people who came remembered the kilns and the firing schedules and the Al-Simag brand name and the quiet pride of making something that worked, something that never failed, something that most people never knew existed. In 1952, at the company's 50th anniversary, employees had received a brochure titled 50 Years of Progress, a picture trip through American Lava Corporation. The photographs in that brochure captured the teamwork and ingenuity that existed at the plant during its peak years. Men and women working side by side, shaping ceramics, loading kilns, inspecting finished parts, boxing them for shipment. The brochure is now a historical artifact, a record of a world that no longer exists.
Today, steatite ceramic insulators are still manufactured worldwide. The material has been supplemented by alumina, zirconia, silicon nitride, and other advanced ceramics that offer higher performance for specialized applications. But steatite remains the workhorse for applications where high-frequency insulation, mechanical strength, and cost-effectiveness are all required. It is in the standoff insulators on broadcast antenna towers that transmit the radio and television signals you receive every day. It is in the heating elements of industrial ovens and furnaces. It is in the terminal blocks of electrical distribution panels in every commercial building. It is in automotive spark plug insulators, thermostat components, sensor housings, and the ceramic substrates that support the circuitry in your car's engine management computer. The transition from vacuum tubes to transistors in the 1960s and to integrated circuits in the 1970s changed the scale of ceramics in electronics but did not eliminate them. Modern circuit boards sit on ceramic substrates. Semiconductor packages use ceramic housings. The chip inside your phone is mounted on a ceramic base that dissipates heat and provides electrical isolation. The frequencies have climbed from megahertz to gigahertz, and the components have shrunk from the size of a thumb to the size of a grain of sand, but the fundamental requirement remains. Something must keep the electricity from going where it should not go, and that something is still, in millions of applications worldwide, a ceramic. The global technical ceramics market is now worth tens of billions of dollars annually. Japan, Germany, China, and the United States are the major producers. Companies like Kyocera, Ceramtech, Coors-Tech, and Morgan Advanced Materials have built global enterprises on the foundation that wartime necessity laid. The materials have changed, the applications have multiplied, and the precision has increased by orders of magnitude. But the fundamental principle is the same as it was in 1942. Wherever electricity flows through a machine, something must prevent it from escaping. The Al-Simag brand is gone now, expired with its trademark in 1994. American Lava Corporation exists only in corporate records and in the memories of the families whose members worked there. The promotional film that the company produced in the 1950s, showing the factory in operation, the kilns glowing, the workers shaping and firing and testing the ceramic parts, has been digitized and archived. It is a record of a world that no longer exists, a world where a small company in Chattanooga, Tennessee, made the invisible components that held the electronic nervous system of the Allied war machine together. Paul Cruzy's company made pieces of fired clay. That is all a ceramic insulator is when you strip away the engineering language and the military specifications and the trade names and the patents. It is clay mixed with minerals, shaped by human hands or pressed by human-operated machines, hardened in fire until the molecular structure fuses into something that was not there before. A material that is not what went into the kiln. The raw ingredients are soft, crumbly, and porous.
What comes out is dense, hard, and impervious. The fire does not just dry the clay, it transforms it. The silicon and magnesium atoms rearrange into a crystalline structure that locks in the electrical properties that make the finished product valuable. It is alchemy of the most literal kind, the transmutation of earth into something more useful than earth, achieved not by magic, but by temperature, time, and the knowledge of how minerals behave when heated beyond the point where their atomic structures reorganize. The same basic process that humans have used for 10,000 years to make pots, tiles, and bricks, refined to a precision that allowed it to insulate the circuits that detected enemy aircraft, guided naval gunfire, detonated artillery shells at exactly the right moment, and kept a soldier's radio working in the rain and mud and chaos of combat. The ceramic did not fire a shot. It did not fly a mission. It did not decode a message. It sat inside the machine, invisible and silent, keeping the electricity where it belonged. And because it did that one simple thing, because it did not fail, the machines worked, the signals got through, and the men who depended on those signals lived to see the next day. That is what an insulator does. It keeps things apart that must be kept apart. It is the boundary between function and failure, between a working radio and a dead one, between a circuit that operates and a circuit that burns. And in the Second World War, when every radio mattered and every radar set was the difference between seeing the enemy first and being seen first, the insulator was not a minor component. It was the component that made all the other components possible. Steatite ceramic, a fired piece of magnesium silicate, white as bone, smooth as glass, harder than steel, invisible inside every radio that ever carried a voice across a battlefield. Made in Chattanooga, Tennessee, by women who had left cotton farms for factory floors, fired in kilns that glowed through the night, tested and shipped and installed and forgotten. Forgotten, but never failed. That is the epitaph of the ceramic insulator. Not a weapon, not a hero, not a story anyone tells at reunions or in documentaries. Just a small white piece of fired earth sitting inside a machine doing the one thing it was made to do, keeping the current where it belongs, keeping the signal clean, keeping the circuit alive. 10,000 years of ceramic craft distilled into a component the size of a thimble, invisible inside every radio that ever carried a voice across a battlefield, every radar that ever saved a ship from a torpedo, every proximity fuse that ever burst a shell at the exact altitude where the shrapnel would do the most damage. Made in Chattanooga, fired in kilns that glowed through the night, tested, shipped, installed, and forgotten. Forgotten, but never failed.